Okay, we wait for Clarice join and then we continue. Clarice, is your line okay? 那个声音有断断的。Okay, yeah, for your information, I've recorded down the lessons. So I'll share in the group later also. Right, so let's continue. Okay, escape velocity. Now, okay, let me position this a bit. Okay. Now we know that every time you throw something, it will always come back. Okay. Suppose that I throw an object, giving it an initial velocity u. Okay. From here, I throw it up, u. The moment it rises, going up, there's a gravitational acceleration acting, right? So where is the direction? Is downwards. Downwards. So we have A downwards. And this, considering that they are very close to the surface of the Earth, this is 10. Okay, I just take 10. Okay, so meaning that as it rises, its velocity minus 10, minus 10, minus 10, minus 10. Eventually, at one point, the V would be 0. At this height, the object stops momentarily. Okay, and the object stops, but the force does not stop. The gravitational force pulling the object downward will not stop. It is acting continuously. Okay, so here, when the object stops and force is still acting downward, so the object will start to accelerate downward and then it will fall back down. But we don't want it to fall back down. We want the object to escape from the gravitational pull of the Earth. Right? So this time, the second time, I try it again. I try it again and I increase my initial velocity. Okay, so here, I try U2 and it's going in this way. This time it reached much higher altitude. Here, every second, again, minus 10, minus 10, minus 10. If I give it an initial velocity of 1000 meter per second, every second, minus 10, minus 10, minus 10, it takes about 100 seconds to reach velocity 0. So it will rise 100 seconds and then it will stop again. I give it 10,000 meter per second velocity. It rises for 1000 seconds before coming to a temporary stop up there. And then when it stops up there, what happened? It will check whether is there still G acting on the object at that position. is there still G, or is there still gravitational forces acting? If there's still gravitational forces acting when it stops, then again, it will accelerate back down and fall back down onto the Earth. So second attempt, we fell again. Now, third attempt, again, I try again. This time, I increase much more the velocity. Initial velocity, I increase U3. Okay, this time it travels further up. The distance becomes significant, the altitude becomes significant, that the gravitational field strength starts to decrease. Okay, again, at surface, what is your G? 10, right? So at 100 kilometer or few hundred kilometer, the G is still 10. Okay, it barely changes. But if the height becomes so much that the G starts to decrease, here, G become 7. Here, G become 3. Okay, now here U3, velocity decrease, decrease, decrease together with the G. The G also decrease. Okay, so velocity decrease until here, velocity equals to 0. The moment when the velocity equals to 0, check the G again. Is the G still there? Yes, the G is still there, but it's smaller value, right? The value becomes smaller. Now the G becomes 3 already. Is there still force acting? Yes, there's still forces, because G3 means 3 Newton per kg, right? If this thing is 1 kg, then at this point, there would be 3 Newton pulling it downward. Even though there's only 3 Newton is enough to pull it down, because at this point, the velocity already hit 0. There's no more fuel for the object to go further. Okay, so even though it's as small as 1 Newton, it can pull it back down. Okay, so again, it will fall back down. Now, I increase the velocity again, the 4th time, goes further out until here. Okay, U4. Rise, rise, rise. The velocity decrease, decrease, decrease until here where it hits 0. At the same time, the G also hits 0. Okay, so when it hits 0, the G is 0 means that the acceleration would be 0 at this point. There will be no force acting on the object at this altitude. What happens to the object? Because the velocity already 0, right? So the object will not move further. It will not continue to move further. Okay, but it also will not fall back down because the G already 0. Okay, so at this stage is where a point that is an equilibrium. Okay, balance. It will not fall back down, and it will not go further. Okay, now from here we can see G decreases, then G5, G3, G eventually reach 0. So the U, which U? I got 4 U here, U1, U2, U3, U4. Focus on U4. U4 is the velocity that causes the object to go out until the G is 0. This U4, we call it what? This U4, we call it the escape velocity. Okay, now how do you define escape velocity? Here you define it. Escape velocity of a planet, okay, is that minimum velocity of a planet. Oh, sorry, is that minimum velocity given? Okay, this is how we define it. Escape velocity of a planet is the minimum velocity given. Take note of the word minimum velocity, okay? Is the minimum velocity given to the object due to which it will not come back again. It is the U4. It has to be exactly the velocity that just enough, just sufficient to let it escape and never come back. It need not to go further, but it must not fall back down. Okay, remember, it need not to go further, but it must not fall back down. That is the minimum velocity there. Now you see, suppose that I launch it again this time. I try it again, but this time I'm going to take much more velocity, greater than this U4. Okay, U5. Let's say U4 is 3000, just an example, okay? 3000 meter per second. And U5, I launch it with 4000 meter per second. Will it escape the Earth? Yes, it will escape, right? So it will go out, further out. And then here, G is 10, G5, G3, G0. And at G0, what happens to the velocity of the object? The velocity still got left over. The object still got leftover velocity because it's higher than 3000, right? If 3000 is the velocity that just sufficient to reach here, then if you feed it with 4000, then it will have extra velocity. Okay, when G is 0, here the object has extra velocity, it can go further. So it will continue to travel and it will move away from the Earth, it will continue to travel into space. Now, this U5 is the velocity that also allow the object to escape, right? But can we call it escape velocity? This one. Be very clear, this we cannot call it escape velocity. This is the escape velocity. This is the escape velocity, the 3000. Even though 4000, you can send it away, but we don't call it escape. Why? Because escape velocity is the velocity just sufficient, just enough to make the object escape and don't fall back down. Okay, remember that. Okay. Now, how do we calculate this escape velocity? That's the question. Calculation of escape velocity, we use the concept of energy. Okay, concept of energy. Now, in energy, there's a law called the conservation of energy, just like conservation of momentum. Okay, if you remember, what is conservation of momentum? Total momentum before 等于 total momentum after, provided there's no external force, right? So conservation of energy is the same thing. Total energy before means that when you launch it, you're giving it energy. What is the energy? Speed, kinetic. Okay, so Ke. Kinetic energy is due to motion, 也就是 speed 啦。如果你有 speed, then you have kinetic energy. If you're not moving, then you don't have kinetic energy. So when I throw it, I'm giving it maximum kinetic energy. Why maximum? Because the moment I throw it, that is the largest velocity. As it goes up, the velocity starts to decrease, right? So as it decreases, the kinetic energy will decrease. So where is the maximum? Is it up there or is it down here? It's down here, maximum kinetic energy. The moment I throw it is maximum. Okay, so kinetic energy, how about at the top? When it rises at the maximum height, it stops momentarily, right? V is 0. So at this particular instance of time, the Ke would be 0. Now, if I sketch this, you see, from here, go up here. At ground, what is the Ke? Ke is maximum. We can calculate that. The formula is half mv squared. Okay, half mv squared. I'm not sure if you're familiar with this one because you have the energy chapter is in your senior 2, but I don't know if you have learned this in your previous like form 3. Half mv squared. Okay, this is the formula for the kinetic energy. Okay, now at ground. Now at the top where V is 0. So what is the Ke? The kinetic energy here would be 0. From here to here, going up, the Ke decreases because it loses speed. If I ask you, what is the Ke lost? What is the loss of kinetic energy? What is the decrease in kinetic energy? What is the value? Let's say here is 100. joule. Going up, it becomes 0 joule. Maximum is 100, right? Going up, it decreases down to 0. If I ask what is the decrease, how much is the decrease? 100. 100 is the loss. So the loss of the Ke is whatever the value of the maximum. Okay, so Ke loss is equals to half mv squared. That's the first one. The amount of the kinetic energy loss during the motion going up is equals to half mv squared. What is this v? The v is the v at ground, which is the escape velocity, right? VE, I'll call it VE. The escape velocity. That's the U4. This one, 3000 U4. Okay. Escape velocity. Now, maybe you ask, if the kinetic energy is like dissipating into the surrounding, then where it goes? Where it goes? It goes into the potential energy. Okay, so PE stands for potential energy. It is what? It is the energy due to height. 高度 ，OK， 越高，你的 potential energy 越大。Okay, so at ground, again, we look at the potential energy at ground and at the top. At ground, the potential energy would be minimum. Okay, as it gains altitude at the top, the potential energy would be maximum. Here is PE max. Here is PE minimum. Okay, now remember that the Ke, the kinetic energy loss, right, is being converted to the potential energy. When it is going up, kinetic energy minus. At the same time, the potential energy plus. If the Ke minus 10, the PE plus 10. Going up again, the Ke minus 20, the PE plus 20 has to be the same. The amount of the decrease has to be the amount of the increase in the energy. That is conservation of energy. Okay, that is conservation of energy. So at the ground, guys, okay, listen here. At the ground, you got no potential energy, right? It's maximum kinetic energy at the ground. Up there, all the kinetic energy has been converted to potential energy. I repeat, at the ground, you have maximum kinetic energy, no potential energy, because there's zero height, right? Zero height. Up there, you have maximum height, but you don't have velocity. So up there, you have maximum potential energy and zero kinetic energy. So I can say that the Ke loss has been converted to the potential energy gain. The rest is just formula. Okay, so how do we get this? You see, from here to here, we know that this number is always greater than the number down here, right? Okay, the kinetic energy loss is 100 joule. Let's say it's 100 joule. Then the potential energy gain here should be plus 100 also. Okay, from ground to top, plus 100. Now, plus 100, I can write it in two ways. It can be from 0 joule to 100 joule. That's plus 100, right? Or it can be from negative 100 joule to 0 joule. Okay, again, from 0 to 100, there's an increase of 100 joules of potential energy. From negative 100 to 0, this one, mathematically, also we can say that there's an increase of 100 joule in the potential energy, because initially it was negative, right? So plus 100, you get 0. Still, there is an increase. It just depends on where is our 0 point, where is our reference point, where is our 0 joule located at. Okay, now the thing is, for normie, for astronomy, the potential energy, they like to define it 0 joule when the G is equals to 0. All the scientists, they said, potential energy is 0 when the G is 0. Okay, where is it? We want to know where is it. How high? At the top where G is equals to 0. At this altitude is the 0 joule potential energy. This is their reference point of the 0. If this is 0 point, then down here must be 100 to get a plus 100 joule. Okay, now, so from at the ground, so they define that at the ground, your potential energy is equals to negative GME M over R. This is the formula for your potential energy. Now you know why there's a negative. 你看那个 equation potential energy 为什么会有一个 negative 在前面的？是因为它的 reference point 呢是在上面，所以它下面这边是 negative。Okay, same with this one. This one 呢 ，for this one， 他们 assume 0是在那个 ground level， 上到去100 joule， 所以它增加100。For 这一个，它 assume 那个 0 point 是在上面，所以在 starting 这个 ground level 它是 negative。其实是一样东西来的啦。OK， 只是为什么我跟你讲这个是，只是因为我要给你知道为什么这里会有一个 negative。Okay, why here you got a negative? Okay, now, so negative, what about up here? PE up here would be 0, right? 0 point up here. And from here to here, there's a plus 100. So we write what is the potential energy gain? 加多少？我们用上面减掉下面，零减这一个。Okay, so potential energy gain 就是它的相差嘛，对不对？它的相差我就用0哦，零就是上面那边，我减掉，再减这个 GME over MR， 这个两个边加，所以我拿回一样的东西，只是没有 negative。This is the potential energy gain. GME M over R. Okay, formula for potential energy, this one. Equation 1. This is the formula for potential energy. Initially, there will be a negative. There's a negative. Okay, negative potential energy. Because at ground level, they define it as negative. And up there is 0 point. Okay, now, from here, we know that kinetic energy loss 是等于 potential energy gain. This expression, please remember this. Kinetic energy loss during the motion going up will be equals to K gain. 100 joule loss would be 100 joule gain. So I can write in terms of equation, okay? In terms of equation, I write half mv E square. 这个是这个来的嘛，对不对？ Ke loss 等于 GME M over R. So from here, simplify. M cross out with M. Okay, so V E square equals to 2GME over R. And then VE equals to square root of 2GME over R. Here you get your escape velocity. Equation number 2. What are the constant? G is constant. ME is constant. Radius of the Earth also a constant. So the velocity depends on what? The escape velocity of a planet depends on the mass of the planet, depend on the radius of the planet. 你看到这个 capital R 是 planet 的 radius 啊，不是那个高度啊，不是 altitude 啊。The small r is the altitude. The big R is the radius of the planet. So the bigger the planet, the higher will be the escape velocity, which means that object has to reach higher velocity to be able to escape from the planet. Earth and Jupiter, if you launch the same object, which one will have more struggle to escape from the planet, to escape the planet? Jupiter, because higher mass and higher radius of the planet. Okay, can you calculate the velocity? Yes, you can. You just put in the values. You know already all the values. G, you know, ME already is given to you all the time. R also is given to you. You can easily calculate your VE, your escape velocity. Now, to simplify things, you see, we get from here, VE 等于 2gm E over R, 对吗 ？OK, VE 等于 square root 2乘 GME， 我再乘多一个 R square 乘 R。Okay, I put extra R here. So when you cut off this one, it's still the same. You get this one, the same thing. Okay, and then we put VE equals to 2 times, what is this? This is your G. GR. So escape velocity equals to GR. That is your equation. You can use this 1, or you can use this 2. This one simpler. You just put in whatever the G value, whatever the R, then you get the escape velocity of the planet. Okay, so again, what is escape velocity? The velocity that is just enough to send the object into outer space without falling down. Not necessarily it has to go away, as long as it is not falling down. That velocity is called the minimum velocity to send it escape. Okay, so overall, just to give you a summarize of the list of formula. So we talk about period, 2 pi r, this is the period of the satellite, given the radius and the velocity of the satellite. And then also you might need to use this period, 2 pi square root r cube GME. Second one. Okay, 有时候 question 叫你找 mass 的时候啊，你看到他讲 okay, find the mass of the sun given of the orbital radius of the period, then you know you need to use this. Okay, because here you got the M. Maybe this one I don't write ME, this one I write it. This is the central object, and the T here is the orbiting object. Okay, Earth around sun, the M would be the sun, the T would be the Earth, the R also the Earth, the mean distance of the Earth. So this one not only allows you to find the period, you can also work backwards to find the mass of the central planet. A lot of questions will ask you, they will ask you, okay, find the mass this, especially the Kepler's third law. Okay. And then what else? What formula? Okay, we got 1, 2 already, right? And then we got the V equals to GME over R. 这个是什么？这个是 satellite speed. To keep in orbit. Okay, if I make it more general, then I can say that this M is again the central object, and the V is the speed of, sorry, let me rephrase this for you. The speed of orbiting object to maintain in orbit. Okay. Usually they use this for satellite. Okay, find the speed of the satellite to maintain in orbit. We use this formula. But if I want to make it more general, so that in all situations you can use, okay, the M would be the central object, and the V would be the orbiting object. Okay, orbiting object. So you are finding the speed of the orbiting object around the central object. Okay, you got 2 already, you got 3 already, and the last one is, just now we talk about the escape velocity, right? The escape velocity. So VE 等于 VE 就是等于 square of GM over R. Okay, this one we put Earth lah, okay? R, ME, the mass of Earth, the radius of Earth. This is for satellite. 这个 V 跟这个 V 不一样啊，不要弄乱啊。这个 V escape velocity， 这个 V 是 orbital velocity. 然后 yeah, this is the general one. Okay, number 3, this is number 3, and this is number 4. Finally, you also need to know the centripetal acceleration. A equals to V squared over R. This V is what V? This V is the number 3. V equals to square root GM over R. It is this V. Not the escape velocity. Okay, that's the centripetal acceleration. What is the escape velocity for the Earth? VE 等于2GR。Okay， 我们可以算2乘 9.8 乘 radius 是6400 meter， 等于 11.2 kilometer per second. That is the escape velocity of the Earth. Is it a fixed value? Yes, it is a fixed value. 11.2 km per second. Meaning that if you want to escape Earth, you need to be traveling at 1 second, you need to go 11.2 km. In 1 second, you need to go that fast. Your rocket, you have to make sure it achieves this speed. You don't want your rocket to go halfway and then take a U-turn down here. So you have to make sure it exceeds the minimum requirement, the escape velocity. Okay, so basically that's it for the gravitation. The rest is practice, practice, and practice. And also be careful because in gravitation, right, you are dealing with a lot of large number. 那种 value 都是很大的 10 power of 24 or something like that. So you have to be careful. Okay, be careful when you calculate large numbers. Use bracket in your calculator. Also be careful of the power. And also again, change unit. A lot of careless mistakes is because of unit in gravitation. So like radius 6400 km, change to meter. Always want to change the unit, especially when we are dealing with the mean distance of the Earth and the Sun. What is the mean distance? 1.97. I forgot already. Okay, it's given like usually it's given. It's a very big number times 10 to the power of. I don't remember this. Okay, never mind. All right, so guys, I will send you a few exercises on the escape velocity and satellites. Okay, and for the previous exercises, if you have questions, WhatsApp me or let me know in the chat. For the previous exercises like the Kepler's law. Okay, we have less than 1 minute. I'll create one more meeting.